Hello friends, welcome back to my YouTube channel. So in last video we have seen the working procedure of the flexibility method. So today we'll solve a problem on that. So this is the given problem. So now we'll solve a problem on that. The given problem is like this. Develop the flexibility matrix for the given coordinates. Here the coordinates are given. Coordinate 1 and coordinate 2 are given in problem. So by using this coordinate we'll develop the flexibility matrix. So here we have to redraw the diagram like this. So now I am calculating the reaction for coordinate 1. So removing all the loads. So I will take only coordinate number 1. On that unit load is acting, that is 1 kilonewton. So here also distance 3 meter, here also 3 meter. So now we have to calculate the reactions for this. For each coordinate we need to calculate the reactions separately. So now I am calculating for the coordinate number 1. So by removing all the loads and we only apply the coordinate 1, and here coordinate 1 is nothing but our vertical load of 1 kilonewton which is acting on center of the beam, and here reaction RA takes place, and here one more support is there, that is in the support, draw it, and here reaction RB will takes place. So now we need to find the reactions RA and RB for this diagram. So summation of all the moment is equal to 0. Clockwise we need to take the positive. Here RB is moving upward, so it is anti-clockwise. It means minus RB into distance is from here to here is 6 meter. 3 into 3 6. So minus RB into 6 plus here unit load of 1 kilonewton is acting at a distance of 3 meter. So 1 into 3. So now simplify it. It will come out as RB is equal to 0.5. So it is positive. So now similarly for summation of all the vertical forces is equal to 0. Upward we need to take the positive. Here RA and RB are moving upward. So RA plus RB value we got was 0.5. Put that value. And here one more. So here 1 unit load of 1 kilonewton is acting. It is moving downward. So it means it is negative. We need to take the minus 1 is equal to 0. So now simplify it. So our RA will come out as 0.5 minus 1 will be 0.5. So it is 0.5, it is also 0.5. So this is for the first diagram, coordinate number 1. So now similarly for the coordinate number 2, the moment is acting. Again we need to draw the diagram separately. We need to apply moment of 1 kilonewton, and this is point B, this is point A. Here also 3 meter, here also 3 meter. So now take summation of all the moment about A is equal to 0. Clockwise we need to take the positive. So here reaction RA takes place and here RB takes place. So RB is moving anti-clockwise at a distance of 6 meters. So minus RB into 6 plus here unit moment of 1 kilonewton is acting. It is clockwise. So plus 1 is equal to 0. So now simplify it. Our RB will come out as 0.16. So now summation of all the vertical forces is equal to 0. Upward we need to take the positive. So here RA and RB are the upward forces. So RA plus RB is equal to 0. RA plus RB we got was 0.16. So now put that value. If I take the right side, it will become minus. So minus 0.16 is the answer. So it is moving downward. So it means whatever we have here negative sign, what it indicates is the upward direction that you gave is wrong. So make it as downward. We have assumed the direction for RA upward is wrong. It means the negative sign indicates we have the direction which we have assumed for reaction RA is wrong. So it is moving downward. So make it as downward. So minus 0.16. Here it is correct and here it is 0.16. It is correct. The direction is correct. So this is how we need to calculate the reaction for each coordinate separately. And next is we have to draw a table of unit load methods. So the table will come like this. So this is the first column as the members, and second is origin and limit, moment, and moment 1 m1 and moment 2 m2. So now we'll see the how to fill this table. For member AC, so see here, this is the point C, member AC. So the origin for AC, I am taking origin as A, and limit is here, the distance is 3 meter, no, so 0 to 3 I am taking, limit is 0 to 3. And for m1, moment of coordinate 1, so for AC I have taken the origin A. If I cut the section xx far away from the origin A, so at a distance of x, so xx, section xx at a distance of x from the origin. So here our m1 becomes, so our intensity is 0.5 or 0.5 into x. So it is moving, so upward section, above the section we need to take the positive, the forces which is moving above the section we need to take the positive. So 0.5 into x at a distance of x, here intensity is 0.5. and similarly, so this diagram will call it as a m1 bending moment of coordinate 1, this is called m2 bending moment of coordinate number 2. And for m2 we need to see the diagram number 2, cut the section far away from the origin A at a distance of x, and your intensity is minus 0.16, it is downward at a distance of x, so m2 is minus 0.16 into x. So this is our m2. This is how we need to find the m1 and m2. So here one more thing I want to tell you. See here, when you calculating for the member AC, we need to take only this portion. Remaining is we need to hide it. Take only this portion. While calculating the moment for this also hide this. Take only this much off from here to here, AC part. So yes, we will calculate for member CB. For member CB, I have taken the origin as B, and limit is 0 to 3 limit, and from here to here to calculate the m1, so I am taking the origin as B, no, so here we need to cut the section x-axis far away from the origin B. So this is the section x-axis at a distance of x from origin B. So your intensity is 0.5 into x. So it is going upward. So upward means it is positive. So forces which are moving upside the section we need to take the positive. So 0.5 into x, and m1 is 0.5 into x. Similarly for m2, our origin is B, we have taken, no. So if you cut the section x-axis far away from the origin B, x-axis at a distance of x from the origin, here intensity is 0.15, so it is also moving upward, so positive 0.16 into x at a distance of x. This is our m2 for the member CB. So here now we have calculate the moment for each member. Next we have to calculate the flexibility matrix. So by using the formula, so which I have shown in while explaining the working procedure, that is delta is equal to F11 F12. So now we are calculating for the matrix 2 into 2 matrix. So we need to take the delta is equal to F11. I will write here delta is equal to F11 F12 F21 and F22. So for find outing the F11, we have the separate formula for that. So for F11 we have the formula, see here, for F11 we have the formula F11 is equal to integration of 0 to L m1 square divided by EI into dx. This is for F11. So now we will calculate F11 is equal to integration of 0 to L m1 square divided by EI into dx. So here our substitute all the value. M1 is for member AC, we will calculate now. calculate for both the member. 0 to integration of 0, limit is 0 to 3 and m1 is 0.5x and for AC is 0.5x whole square. Here I am taking 1 divided by EI constant outside. 1 divided by EI, it is constant, I am taking outside. 0.5x whole square dx plus for CB also limit is 0 to 3 and 0.5x moment is 0.5x whole square into dx. So now by using calci we will solve it. F11 is equal to, so here integration of limit is 0 to 3, so 0 to 3 0.5x whole square plus integration of again 0 to 3 limit 0 to 3 and 0.5x whole square 0.5x whole square. So now solve it. So our F11 will come out as 4.5. Write it here. F11 is equal to 4.5 divided by EI. Similarly, we will calculate for the F22. So we have the formula for that. Integration of 0 to L m2 square divided by EI into dx. So now 0 to L m2 square divided by EI into dx. So now 1 divided by EI is constant, I am taking outside. 0 to 3 limit is 0 to 3 and for m2 for member AC minus 0.16x whole square dx. For member CB 0 to 3 limit and moment is 0.16x whole square into dx. So now by using calci we will solve it. So integration of limit is again 0 to 3. Substitute all the value. So integration is 0 to 3 minus 0.16x whole square plus add one more integration. So plus integration of 0 to 3 limit is 0 to 3 0.16x whole square. So now solve it. So it will come out as 0.46. So our F22 value is 0.42. 0.46 divided by EI. So similarly we will calculate for the F21 and F12. For that F21 and we have the formula. So we have same formula for F12 and F21. Integration of 0 to L m1 m2 divided by EI into dx. By using this formula we will calculate the F12 and 21. So limit is 0 to L m1 m2 divided by EI into dx. So now we need to substitute all the value. So 1 divided by EI is constant, I am taking outside. Limit is 0 to 3. So m1 value for AC is 0.5x and minus 0.16x. m2 value is 0.5x and m2 value is minus 0.16x into dx. For similarly for member CB we need to put integration of 0 to 3 and the value is for member CB 0.5x into 0.5x into 0.16x dx. So now solve it by using calci. Integration of 0 to 3 into 0.5x into minus 0.16x and plus one more is there, add it, integration of 0 to 3 and into 0.5x 0.5x into 0.16 now solve it, so it will come out as 0. Answer is 0. f12 and f21 value will be 0. So this is how we need to find all the elements. So now substitute all the value here. f11 value we got was 4.5 divided by ei. 4.5 divided by ei. I am taking ei outside. So and f2 value is 0.46. f22 value is 0.46. f21 and f12 value is 0. I am taking ei outside. So this is how we need to develop the flexibility matrix for the given coordinate. So I hope you all are understood. So if you like the video, like it, share it and subscribe for the more videos. Thank you for watching.